All right, good morning. I did post a note and the daily problem for 3.6 on Canvas, and I did go ahead and open up the rest of the weeks, the modules on Canvas, so that you can see that we will be able to cover everything. We're just going to have to do a little bit of extra work. Instead of covering maybe like 2 sections, we will be able to finish everything if we do about 3 sections a week. And that is doable because I definitely want to cover all integrations before May 7th. Speaking of May 7th is your final exam day, and according to the official final exam calendar, our exam does start at 8 o'clock, but you do need to make sure that you need to make your decision soon about whether you want the letter grade or just a P plus or P minus grade, and submit that form, because after I have your final grade, final exam grades, I think I have about like 2 days to submit the final the course grade. So but start thinking about that for me, please, and email me if you have any questions. I did went ahead and changed the grade book to just show P plus and P minus, so you may need to go and I think you will be able to see your numerical grades if you use the laptop or computer to go in. But on iPad, when I try to see somebody's grade, it only sees the P plus or P minus. But if you have any questions on your grade, let me know. Speaking of grades, we will talk about exam 3 and the final exam soon. But I still have about 9 exam 2 to grade. 25 of you got your exam grades already. And if you want to know why you got 97 or 98 instead of 100, if you're wondering where did I lose that extra point, you should be able to click on the assignment and the file. Some of you submitted like 11 picture files or like 1 PDF. But what I did was I looked through each of those files submitted and made comments. So you should be able to look and see why I took points off, because I was trying to be very descriptive when I was grading your exam. So if you wonder about your exam grade, go into Canvas, check out the files and annotations, but you can also email me and we can have a Zoom conference to talk about those. All right, this week, here's the plan for this week. I will have the agenda slide soon, but just wanted to cover the notes first so that you can try this daily problem. I'm going to have 2 daily problems from today. 3.6 and 3.7 are pretty short. So we're going to do those today, Tuesday. And Thursday, 3.8 is not that short. So, on Thursday, we'll just do 3.8. But let's do 3.6 and 3.7 today and 3.8 on Thursday. The daily problem from 3.6 is posted on Canvas for you. I want you to find the decimal approximation of square root of 19. I'm not asking you to use calculator to type in where's my calculator, square root of 19. If you type in square root of 19, you will get 4.358. I'm not asking you to just do that. I want you to use what we are talking about today in this lesson to approximate that. So that's due this Sunday. And if you check out your My Math Lab homework, it's pretty short too. I don't think it shows how many problems you have. I have to be careful because this one has nothing, but sometimes in the middle of recording, I click on an email or I click on a student grade and I have to start all over again. So I'm not going to click on anything, but let's just go ahead and get started on 3.6 notes. This is open. Homework 3.6 is open. It only has about 8 problems. And I try to go over almost all these examples on this note. So after this note, you should be able to just quickly submit that 3.6 daily problem and try those 3.6 My Math Lab homeworks. Okay. So I got 3 learning objectives today. The first one is finding marginal cost, revenue, and profit simply by taking the derivatives of cost, revenue, or profit function. We are going to talk about this new notation, delta y and dy. We'll find them. And we will use differentials for approximation. And this is like the daily problem that you're going to do. I'm going to ask you to find the decimal approximation of square root of 19. And I'll show you examples on how to do those. Okay, so first, let's talk about this new notation called delta notation. Now, you know this guy. You know this f of x plus h minus f of x divided by h. We know this as the difference quotient, right? Now, this is how we use, this is what we use to first define the derivative. We took this guy, we took limit as what approaches 0? H approaches 0, because this is an equation for slope of a secant line. Let me try to draw a graph of what we used to talk about. Say that we have a curve like that, and then I have a point right here, and I point right here. If I want to eventually find the slope of a tangent line that just touches this point right here, remember we had to start by taking 2 points. Okay, right? We had to start by taking 2 points and just move this point really, really, really close to that first point. And eventually, when their distance is almost 0, then we have that instantaneous rate of change, that slope of the tangent line at that point. And now that was an H, what H represented. H, the number H is regarded as the change in X, right? The distance from the first X value to the second X value. As that value got really, really, really close to 0, we call that the slope of the tangent line. Another notation for this change in X is called delta X. So draw a little triangle and X, delta X. And this is called delta notation. We also have delta Y, the change in Y. What we can do is we can take this difference quotient and rewrite using the delta notation, do a couple steps, couple lines, and then we'll be able to get this conclusion. But I'm going to go ahead and give this to you so that we can use it today. If you take a look at the textbook, because you all have access to ebook, on page, let me see, because I feel kind of guilty just using this equation without coming up with it with you guys first. But so I'm going to at least give you the page number. So if you wonder if you want to actually see what's happening, if you take a look at page 336, let me write it, page 336 on your textbook, you will see some work, some symbol work, some rewriting that will take your difference quotient to this conclusion that we're going to actually use today. So let's take a look. The derivative of f of x, f prime of x, is approximately delta y over delta x. The changes in y over changes in x. Now, multiply both sides by delta x. Then what will you get? That delta y is equal to f prime of x times, now they said dx, but dx is delta x, okay? So multiply both sides by delta x. And we're mostly going to work with this second equation here. Then we get delta y is equal to f prime of x times dx, or delta x. We're going to find delta x using this. I'm going to go ahead and highlight this. But if you wonder, where did you get that from? It's very simple. It's just replacing things with symbols and just reworking it out. But take a look at page 336 if you want to know where this little guy came from. But let's use this. But let me give you some definitions first. So for y equals f of x, we define dx, called differential of x, by dx equals delta x. Now, but dy is not really going to be just delta y, but dy is going to be the derivative of f of x times dx. Okay? Alrighty, so if a question asks you to find dy, that's what you're going to have to do. Okay? So just new notation, but everything you've been doing before. So they're not that bad at all. It's just they look so different right now with these delta notation and this dy. But these are called differential of x and differential of y. So let's go over example 1 together. And you'll know, oh, it's not that bad. It's actually very simple. So for y equals f of x, and I have a function 5x to the third power, and x is 2, and delta x is 0.01. So what are we saying? Well, we're starting from x equals 2, but that delta x, we're going to have a change in x of 0.01. So First, let's find delta y for the given x and the delta x value. We want to round to 4 decimal places as needed. So we simply want to find the change in y. So this is what I'm going to do, okay? I'm going to say that x1 is equal to 2. Where did I get that? Well, x is 2. But when they say delta x, that's the change in x, right? I'm going to call x2 2 plus 0.01. So x2 is 2.01. So I got two x values, right? The original x is 2. The new x value is 2.01. What they want you to find is the change in y when when y is equal to 5x to the third power. So I'm going to go ahead and find this. What is the first y value for x of 1? If I plug in 2 into this function, I will get 5 times 2 cubed. That is 5 times 8. We get the first y value to be 40. Okay, the first y value to be 40. I will say y1 is 40. Now let's plug in x2 into our f of x. The second x value, that is 2.01, right? And we got that 2.01 by adding this delta x to the original x, because that's the change in x. If I go ahead and evaluate that, I will get 5 times 2.01 cubed. And what's that going to be? It's going to be your decimal. 5 times 2.01 squared. Oh, whoopsies. Not squared, but cubed is equal to 40.603005, I see. 0, oh dear, 5. Okay, so if they want delta y, they're simply asking you for the change in y. So all you now need to do is just subtract these two y values, and that's it. But later, it may be helpful to have some of these formulas down. So let me go ahead and give you a formula for delta y, okay? Let me look up. Okay, so delta y is equal to f of x plus delta x minus f of x. And that's really what we did, right? Let me color code some of these, okay? Our f of x2 is this right here. Because we got x2 by adding our delta x to the original x value. And then, well, f of x is simply our original f of x1. So without really me giving you this formula, we were able to find out what delta y is, because we know delta y just means the change in y. Let's go ahead and subtract 40.603005 minus 40. We got the delta y to be 0.603. Well, they wanted 4 decimal places, so I'll just put an awkward 0 after it. So that's how you find delta y. You know, it's just slope formula. It's not really slope formula. It's just evaluating functions and subtracting the y values, right? Okay, now let's find dy. Try to make this a little bit smaller. I think I write a little too big. Let's find dy. Dy is equal to f prime of x times dx, right? And that's the formula that I highlighted above there. So let's find what that is. So dy, in order for you to find dy, what you want to do is find dy dx. So our y is what? Y is 5x cubed, right? Okay, y is 5x cubed. Find y prime, but what's another notation for y prime? Take d dx, take the derivative of both sides, okay? And then the left side is now what? dy dx. And the right side, you do know how to take derivative of 5x cubed. That is going to give you what? 15x squared, right? Now we're almost done. They wanted you to multiply both sides by, well, they want you to have dy by itself. So if you multiply both sides by dx, that you will get dy equals 15x squared times dx, right? Now, did they want for this specific x and dx value? I think so, because later, you know what? No. This is where I'm going to stop for part B, because they want you to find the dy for the given x and delta x value on part C. So stop right here for this problem. The answer for B is this. We found the dy, but we left the x and dx alone. But for the last one, C, the dy, find the dy for the given x. Remember, x is 2. And delta x, in other words, dx, was given as what? 0.01. So we'll use what we just found above to find the dy value at x at 2 and dx at 0.1. So plug in x equals 2 and dx of 0.01. Okay? What's that going to be? All right. That is going to be, I'm multiplying on my little scientific calculator, times, I dropped my calculator, 0.01. When I typed that in, I got 0.6. Now notice this number is very, very close to what we got on part A, right? So that's what you can do to answer a question like this. I think I put one like this on your homework, the first question, just so that you can find what dy is, find what delta y is. But that was the first learning objective that I wanted to kind of go over with you, finding the delta y and dy. So we're good with that. But let's do something that has a little more application to it, because like, what does that mean, right? Let's go ahead and go over example 2, and this will connect nicely with the cost and the marginals and the revenue, the second part of this lesson that I want to go over, the more business part of it. All right, example 2, assume that C of x is in dollars, and x is the number of units produced and sold. For the total cost function, so C of x is the total cost function. They gave that to us as this. It's a quadratic function. They want you to find delta C. And so we're doing two things. We first have to find the delta C. And they also want you to find the C prime of x when x is 40 and delta x is 1. Alrighty, how about we find delta x first? Let's find, I call delta x, sorry, delta C first. Okay? So that's going to be the change in cost, right? The change in cost. When x is 40, let me go ahead and find the cost first, okay? What is the cost when they produce 40 units of this? I don't know what this is, but plug in the cost, or plug into the cost function. 0.01 times 40 squared plus 0.4 times 40 plus 20. So you'll do that, right? But delta C is the change in cost. So what's the second cost that we're going to have to figure out? Notice the delta x is 1. So go up 1 and find the cost associated with producing 41 units, okay? So that will be this. How many emails do you guys get every day now? Okay. I wrote it down. I am getting my calculator to type this in so that I can get tool cost. 0.01 times 40 squared plus 0.4 times 40 plus 20. When I plugged in the first cost, I got $52. Okay, I'm going to now very carefully plug in the other one. 41 this time. And when I did that, I got $53.21. So let's find what they wanted. What is delta C? That's going to be 53.21 minus 52, right? So that's going to be $1.21. So that's going to be the change in cost if they go from producing and selling 40 units to 41 units. Okay? They're gonna make $1.21. Well, it's not, they're not going to make, right? It's gonna cost them more. Okay. Now they want you to also find the second part. I'm not done with this problem, looks like. Let me go ahead and just minimize this a little bit. So that was the work on finding delta C. Let's go ahead and find the other one. They also wanted you to find C prime of X. C prime of X. Now, you have our C of X. Let's find the derivative of this cost function. And that will be called, later on, I'll give you a big definition box. The derivative of the cost function is called the marginal cost, okay? Which is the approximate cost of making one extra item, okay? But let's go ahead and find that derivative of C. And when we plug in 40 in there, it should be pretty close, right? Alrighty, if I take the derivative of that, I will get 0.02x plus 0.4, no more x, and the 20 gives us 0. And then let's plug in our x value of 40 in here. So we're finding the instantaneous rate of change at 40. It's gonna be a little different. You know why? Because we were going from 40 to 41 units, but that's still 2 points. We were really doing we're really working with the secant line, but now we're working with the tangent line. So it's not going to be exactly the same, but it better be very close because delta x was only 1. It was very small. So plug in 40 in here. $0.4. What's that going to be? Is that going to be... I make some silly mistakes nowadays with simple multiplication, so I better double check. 0.02 times 40, and then if you add 0.4 to that, you will get a 1.2. I'll say $1.20. So we were off by 1 cent. The right side, what we did with the black color is the derivative is the slope of the tangent line, but then the other one, our delta was 1. And you see how the delta x, when we take that to 0, when we take the limit as delta x or h approaches 0, that's how we define the derivative. So they're pretty close. They're not exactly the same, but that is the application part of number 1, which really didn't make much sense. We just did the math, but that's how it can apply. We can say that if they increase the number of units sold from 40 to 41, the total cost will go up by $1.21. All right, now, example 3, and try one more. This question will go with your daily problem. So I'm going to go over example 3 with you, and then maybe do that one to try one more. And then I may stop the video and come back and re-record on the marginal cost and revenue, because I feel like the longer the video goes, there may be like Something's happening. Sometimes it gets lost. Never gets saved. All right, so let me go example 3 and the square root of 11 problem. Consider the function given by y equals f of x equals square root of x. They want you to first find dy when x is 9 and dx is 1. Okay, write down what dy is. Write down that dy is approximately f prime of x times what? Dx. Okay? Now, where did I get that from? Here we go. What we highlighted over here, dy is the derivative of f of x times dx. So, we're going to use that. And in order for us to use that, we really need to find the derivative of f of x, right? So, f of x is equal to square root of x. But let me rewrite this as x raised to the what power? 1/2 power. What is f prime of x then? Using the power rule, you'll bring down that 1/2. Okay? And then the exponent go down by 1. So you will have negative 1/2. So if you want to rewrite this a little bit, a little better looking, I guess you can write it as 1/2 times square root of x. So we found that the derivative is 1/2x squared. So what I'm going to do is I'm going to substitute this f of x in here. Okay, I'm going to substitute that f of x in here. So dy is approximately 1/2 times square root of x times dx, right? Now notice they actually gave you what they want you to use for x. They want you to use x is 9 and they want you to use x is 1, dx is 1. Okay? So plug in those two values into x and dx. Okay? That's going to give us 1/2 times square root of what number? 9 times, and dx is 1. The change in x is 1. So wonder what they're doing. X was at 9, but they're going up by 1. So later we'll be able to do something like that. But all right, let me finish this. 2/2 times 3 times 1. So that's about 1/6, approximately what? 1.666. Oh, I'm sorry, not 1 point. 0.16, is it? 0.16. Let me double check. What's that? If you divide 1 by 6, is that decimal like 1.16 repeating? Yep. 0.16 repeating 666. Okay. So I don't know what we're going to do with it yet, but you'll see. We found the dy when x is 9 and dx is 1. Now what they're asking you to do is what I want you to be able to do today. Use the result of part A, and we're going to estimate square root of x. Oh, interesting, right? So the one problem that you're going to do for me later, I think is square root of 19. I think I'm going to ask you to do square root of 19. And I'll do one more. I'll do square root of 11 there. But let's go ahead and estimate what square root of 10 is without a calculator, with what we just found on part A. So what we know is this. Since dy is approximately square root of 10 minus square root of 9, we have square root of 10 is approximately square root of 9 plus dy. Okay? Didn't we just find what dy is? And we do know square root of what? 9 is simply 3. And we just found above that dy is approximately 0.16 repeating 66666, right? So therefore, we can approximate square root of 10 to be 3.16 repeating 16666. Now, let's see how close we were, okay? We're going to use the calculator to actually type in square root of 10. So what is square root of 10 on calculator? and we're going to compare it with our estimate. What we got is 3.16666. And type in square root of 10 on your calculator. It's going to be a little different. So when you are doing this homework problem on My Math Lab, and if you just use your calculator, they're going to say, oh, no, you're too accurate. They want you to approximate using this method. So square root of 10 is approximately 3.16227766 repeating, or something like that, not repeating. Now, if you take a look, we only differ from this is different only about like what, 0.004. So I will say we were pretty close, and this method will actually work, right? I want to do one more because that was just one example. And it was kind of set out for us, like what to do. But what if I just throw you your problem like, hey, here's square root of 11, and I want you to approximate it using this method. So we'll try one more, this problem down here, and then I will ask you to try the daily problem and submit that, okay? All right, let's start this one. I kind of worded it the same as how you're going to see on your homework. Use that delta y is approximately derivative of f of x times delta x to find the decimal approximation of the radical expression. They want you to round to 3 decimal places as needed. Now, square root of 11. Now, here's the thing. Let y equals, first write down the function that we're going to use. Y is square root of x. That's the function that we're going to use. But notice, what do we know? What's the closest perfect square to 11? How about square root of 9, right? We do know that square root of 9 is exactly 3, but how far away are we? So what I'm going to say is, I'm going to say x is 9. I'm going to say x is 9, okay? So that I can do square root of 9. But delta x, let's call delta x, or in the other word, what? Dx is how far away are we from 11, from 9, 1, 2, right? So delta x is going to be 2. So identify those two first, okay? And why did I pick x equals 9? Because square root of 9 is just 3, and we know that one without really typing anything into our calculator. So we're going to use those two, and let's find the derivative of this function first. So find dy dx, which we just found it above, is 1/2 times x to the negative 1/2, which kind of simplified to 1/2 times square root of x, right? So we got the differential dy to be 1/2 times square root of x times dx. We're going to use this differential, okay, the change in y. Plug in what we know. We know that x is 9 and delta x is 2. Because 9 plus 2 is 11, we pick delta x to be 2. So let's plug in these two numbers, 9 and 2, into x and dx and find that differential, okay? So dy equals 1/2 times square root of 9 times 2 this time. So I will get 1/2 times 3 times 2, and if I get that, I'll get 1/3, which is approximately 0.3333. So difference in y is 0.3333. So what are we going to do? We're going to go ahead and rewrite it. Since dy is, let me change the color here. Since dy is approximately square root of 11 minus square root of 9, we have square root of 11 is approximately square root of 9 plus dy, okay? And what we got is that square root of 9 is simply 3, and we just found dy to be 0.3 repeating, right? So what we can approximate is that square root of 11 is approximately 3.3 repeating. Now, on the calculator, let's use the calculator to see how close we were. Type in square root of 11. what is square root of 11? And that gives us 3.316. 3.316. And it's pretty close to 3.316 what we got, right? So you don't have to check on the calculator. You can definitely just, stop after doing your dy and adding it to the perfect square value. But I want you to try this. It's very similar. The number that I'm giving you, I believe, is square root of 19. So what's the x value and what's the dx value or delta x that you're going to use there? We can do another one if you want me to. Please just email me. But I'm going to go ahead and kind of stop this one right here. And then I'll let you try the daily problem. And then I'll come back and finish this